Hello all, this is Jason Hernsberger, and I wanted to take a few minutes to go over some information with you. I've been doing some research on my own and wanted to share some of that. So, the purpose of this is to go over kind of some attack package data, and so that we're all on the same page, I just wanted to define that. This is going to be a very brief, high level overview of this topic. I'd really like to drill down more in greater detail with anyone who has an interest, but I'm going to try and keep this as short as I can. For the purposes of this, the definition of an attack package is the components of fire suppression delivery that includes pumping equipment, hoses, appliances, and nozzles that all work together to make a stream. My objectives here is to determine what strengths and weaknesses we have with our current fire attack package, and then I'd like to do some testing on some different components and look at some research from what some other places have done and see if it might make a better fit for us. Like I said, I started this project. I came across a couple of articles of interest, and the more research I started doing, getting off more studies and articles and different things that I printed off, and ended up with a full binder of information. So, again, I just want to. A lot of the information that I came across really hit me hard and kind of moved me to try and share with others what I can. And a lot of this goes back to several years ago. We did the rollout of the UL NIST studies of the research and the tactical implications thereof. And this is kind of an extension of that. The research represents an area that we really didn't pay a great deal of attention to at that time. But in hindsight, I think there are things that we can modify to our attack package that might help us achieve a more efficient and effective suppression goal. This is one of the slides that we did in our UL NIST study, talking about the different factors of the modern day fire environment, how we need to change our tactics, change our thought processes, things like that. So this is just kind of going in line with that goal that we started a few years ago. And just as a review, we've spent time again in the past going over the UL NIST stuffs, pondering ways to how we can increase our tactical effectiveness given the new realities of the modern fire environment. One of the takeaways from the research at that time was to focus on getting a lot of water on the fire fast. To achieve this, we want to deploy lines efficiently into the proper positions and ensure that we have ample flow rates to encounter the high BTUs produced by the modern fire environment. In our case at the Woodlands, we've added the use of 2-inch hose as an alternative to 1 3/4, and our nozzles are capable of flowing up to in excess of 250 gallons of water per minute. But it warrants a discussion, I think, of the changing technologies that have allowed for these increases in flow rates. Just because a hose line and a nozzle is physically capable of flowing a given amount of water, is it reasonable that we can achieve those flow rates without in some ways compromising safety, efficiency, or effectiveness? And to introduce that, I think one of the things that we've left out has been the impact of nozzle reaction. So to evaluate this, I want to take a closer look at the concept of nozzle reaction. Paul Grimwood is one of the leading experts in fire stream management and hose advancement operations. One particular study of his that's referenced in a lot of fire stream publications sought to determine the amount of nozzle reaction that could be handled by teams of firefighters, and he came up with this list: 1 firefighter 60 pounds, 2 is 75, and 3 is 95. And our current setup at 175 GPMs is on the verge of being too much for 2 firefighters to handle, much less 1. David Furnell on the American side, he actually wrote the textbook, the Fire Stream Management Handbook, and he has similar research, although in his studies he shows that a single well-trained firefighter can alone manage up to a 70-pound nozzle reaction. And then the hose is a big component of it. Been reading a lot up on Dennis Laguerre, and he's got some really interesting information about how hose has changed over the last 20 to 30 years. Uh, in competition with each other, they've changed their standards, and the hose that we ended up with now is actually larger than is what's specified, which means it's heavier, and it leads to very different real-world measurements from theory to practice. NFPA 1710 is the standard that sets minimum flow requirements for structure firefighting. It stipulates that the first two lines engaged should flow a combined total of no less than 300 GPM. As such, a lot of agencies have set a minimum single line flow rate of 150 to meet this requirement. However, we got to keep in mind that appliances and hose kinks can negatively impact flow rates, so we want to make sure that we exceed this minimum by some range. And also, given that we currently employ automatic nozzles in our system, we need to be aware that kinks or pumping issues may not be realized at the nozzle due to the compensatory mechanism of the nozzle. It'll still provide a nice looking stream, but we may not be getting the flows that we are expecting. So this is our current setup. We employ an automatic nozzle. It has some attributes with it that a lot of the industry experts that are publishing articles and studies have some warnings about this type of nozzle. Even though our nozzles operate at a lower pressure than the legacy automatics, which operated at 100 psi, they still have some drawbacks for structural firefighting. They're the heaviest type of firefighting nozzle there is. Because of this, they're susceptible to the physics of hose whip, tip agitation. They have the most complex construction. They have an internal compensatory spring mechanism that requires periodic maintenance. There's a link here to that maintenance manual. It's about 11 pages of just instructions on how to maintain this nozzle. But perhaps most importantly, the action with the spring and the moving parts may mask flow restrictions upstream by providing a good quality looking stream, but that could present problems if we're advancing them into a hostile environment. And I'll take a look at a couple of things. This is the nozzle flow and reaction chart that TFT puts out. If you look at this chart, you can see that assuming no kinks in the system, a pump discharge pressure in the 150 to 175 range will produce flows of around 156 to 175 GPM. So with a minimum NFPA flow rate of 150, we're barely achieving minimums at that 150 pump pressure. Even so, we're above the 60 or 70 pounds of reaction force that a single firefighter can be expected to effectively manage. If we move over to the 2-inch hose, we have even higher flows, but the nozzle reaction is actually beyond what Grimwood states that 3 people can manage, much less 1 or 2. So this calls into question whether this type of nozzle should be used on the 2-inch lines at all or not. So I guess this is essentially a statement of problem. What can we do to achieve a reasonable and manageable flow rate for an attack line? And the only way that we can reduce nozzle reaction is to either reduce pressure or reduce flow. One notable trend that I've been seeing in the fire service involves the use of a low pressure fixed flow fog nozzle, unlike an automatic. Other departments are actually going back to the simplicity of the smoothbore option, and given the fact that a lot of the UL NIST stuff says that interior structure firefighting should be operated on a smoothbore or straight stream pattern only, that actually becomes a interesting possibility. The fixed flow fog nozzle operates the same way that fogs that we are used to, but it uses a fixed orifice size that's engineered to have an optimum flow rate for a given pre-designated pressure. Without a compensatory spring pressure control system, it's pumped by the pump operator in order to achieve that specific flow rate. It's the same in principle as operating a smoothbore system, but pressure and flow settings are set by the user, and they can be matched up to the same flow rate and pressure to a corresponding smoothbore tip. For example, the nozzle you see on the left can be set for 185 GPM at 50 psi, which is the exact same performance characteristics of a 15/16 inch smoothbore tip. Although such a tip can be specified on a standalone nozzle, it can also be set up as shown here in a break-apart design. A shutoff with an 1 3/8 inch waterway and a full round stainless ball can be fitted with the operator's choice of tip. And then, of course, all major nozzle manufacturers can offer this as an option. This is the TFT. This would be a theoretical Elkhart setup. This is their new XD series that they've come out with. In this conceptual design, we've set the fog tip to 175 GPM at 50 psi, which only gives us 62 pounds of nozzle reaction. On the 15/16 inch smoothbore tip, we have a flow rate of 185 achieved with a nozzle reaction of 68 pounds. So these are noticeably improved over our current setup. Consider how frequently a nozzle operator in our department may have to either stop flowing to move the hose or to gate back in order to better manage everything. Anytime we're either not flowing or gating back, water is not flowing at its intended and designed intended rate. So our working hypothesis is that if we look to transition from automatic nozzles to a break-apart style that gives us the option of a fixed gallonage fog nozzle or a smoothbore tip, will result in a more manageable hose line that will reduce the firefighter fatigue. This has to be paired up with the right kind of hose. I understand there's already been some goals stated of moving over to a combat ready hose, which is it's actually a 1.88 inch internal diameter hose as opposed to the 1 3/4 inch. But that is set up and designed for low pressures. Our legacy hose is not. So to change out the nozzle without changing out the hose could present some problems. But if we do both, I think we can improve our attack selection, have more manageability, more mobility. I think we'll have easier pump operations for our pump operators because we will be able to use the more traditional calculations and factoring for our intended flow rates. Another thing I don't really want to get into much detail with now, but I would like to spend some time researching the 2-inch versus 2.5-inch hose. Granted that given that the 1 3/4 we use is if this were to happen, we would be kind of going to a more of a 1.88 inch hose. It begs the question of whether or not we might see some benefit from actually adopting 2.5-inch hose again in lieu of the 2-inch hose. I think there's some, and again we can get into a great deal of detail with this at some point in the future, but I think there's some mathematical justifications for it that I'd be happy to talk about. But again, we'll keep things kind of separate. This would be the time where we would have an open discussion and we could really get into the details, nitty-gritty of this. Since I've prepared this as a video type presentation, it doesn't really allow for that. But please reach out to me if you do want to discuss this further. I've got all the documentation, some of the research that I've done. Love to talk about it in greater detail. So I do appreciate you spending the time that you've spent thus far going through this, and we'll hope to hear from you.